Okay, so now what we would like to do is, given this integral, we want to do some dimensional analysis. So we want to study the dimensions of I, and let's call this L to the minus D, which means that I behaves as lambda to the D. And D is called the superficial degree of divergence. Okay. And we'll see in a moment why it's called superficial. So there must be something superficial about it, something that it doesn't quite get right. Okay, so let's try to estimate what D is. Well, just looking at this expression that we've got over here, we've got a total of L integrations, and each of them has dimension D. Okay, so each momentum is L to the minus 1, so ddp is L to the minus D, and we've got L of them. So D is equal to LD. And then for each propagator here, for each line, and we've got one of these lines for each internal line, well, each one has got the dimension of 1 over p squared, which means of length squared. So it will contribute minus 2i. So this just be doing dimensional analysis on the expression that you see above that I have just outlined in a blue box. So a trivial statement, okay? Just dimensional analysis on the blue box. Good. Now there's two equations that I want to draw to use. So here's the first one. So we know that the number of loops is equal to the number of internal lines minus the number of vertices minus 1. Now, where did this formula come from? We've seen it before. Well, we said the number of integrations we need to do, which is the number of loops, is the number of independent internal momenta. We also said that each vertex on the Feynman diagram comes with a delta function that's going to relate internal momenta. So it'll be a condition among the internal momenta. But one of the conditions coming from the delta function corresponds to conserving overall energy momentum, and that corresponds to a condition on the external momenta. So of the n delta function conditions that we get, one for each vertex, one of them constrains the external momenta, and n minus one of them constrain the internal momenta. So that's where this formula comes from. And it's very easy to illustrate. So let's take this diagram, okay? And I don't know, let's do this, okay? Let's study this. So if we were studying this diagram, so the number of loops is clearly 4. There's a total of 4 different loops there. So there's 1, 2, 3, 4. So there are the 4 loops, okay? Then we have, in addition, 7 internal lines. So count those. Those are pretty easy. And we've got 4 vertices. So that's also pretty easy. And the equation that we've just written down says 4 is equal to 7 minus 4 minus 1. And that, of course, is a true equation. So it's very easy to check this equation. And that's, in fact, a perfect equation. Now, there's another equation that I want to derive. And it says the following. So first of all, it says n times by r. So what is this? N is the number of vertices, and r is the number of legs at each vertex. What I'm doing here is I'm labeling the points at the vertex that has lines ending on them. So in this diagram that I'm drawing here, I've said r is equal to 4. So each vertex would be associated with 4 dots, okay? So there we go. I'm just drawing these dots here for these endpoints next to the vertex. And here, how many vertices did I have? I had 4 vertices, that's what n was, times by then r was 4, so 16. And if you count, I've got a total of 16 dots. This is equal to, well, each internal line, okay, each internal line runs between 2 red dots, okay? So each internal line connects to 2 of these red dots. So each internal line, actually, let me move that a little bit. Oh, sorry, I didn't mean to do that. Let's redo that. Let me move this just a little. So each internal line connects to two of the red dots. So each internal line is related to two dots. And then plus each external line connects to one of the dots. So plus an external line. So the external lines we've drawn in blue, the internal lines in green, and the endpoints of the vertices in red. So you can see that this identity must be true. If you like, the red dots are places where lines can end. Both endpoints of each internal line ends at a red dot, and one endpoint of the external line ends on a red dot. So this equation is often called the conservation of ends. Conservation of ends. It's counting the endpoints using the vertices or counting the endpoints using the ends of the lines. And this equation over here, let me stress, this holds only if you have a connected Feynman diagram, okay? Let me just make a comment. This is something that you might like to prove. If you have a Feynman diagram with k disconnected pieces, you need a delta function enforcing energy momentum conservation on each of those disconnected pieces. So if there was k disconnected pieces, we would expect L to be I minus n minus k. So you could check that this equation holds, and it's the same logic. K of the delta functions now would be related to conserving, would be related to statements amongst the external momenta. So only I minus n minus k of them would be independent internal loop momenta. Only n minus k of the conditions coming from the vertices would constrain the internal momenta. Okay, so this would be, that was for connected Feynman diagram. This equation is for Feynman diagram with k disconnected graphs. Okay, and you could check that exactly the same way that we just checked the other equation. Good. Okay, so now let's start to use these equations to do something interesting. Okay, I don't think that we need to keep this stuff over here. So let me get rid of it. So we don't need this. Okay, so that can go. And let's remove that as well. Now, okay, so let's first of all solve. So what do I want to do? I think that first of all, we will solve this equation for I. So I will be equal to n times r minus e over 2. And now we're going to plug it into this equation. So L will be equal to nr minus e over 2 minus n plus 1. And now let's plug both of these into D. So D would be equal to D times by L. That will be nr minus e over 2 minus n plus 1. And then we will have minus 2r, which makes it minus nr plus e. Okay, good. So let's just rewrite this a little bit. So D will be equal to, well, we'll have D. Now we've summed that term. Then we will have plus E. And E will be multiplied into 1 minus D over 2. So now we've summed two more terms, that one and that one. And then finally, we will have a term which is proportional to the number of vertices n. And we will have RD over 2, good. that term has gone. We will have minus D minus R. And now that's the minus D, that's the minus R. Good. So this is now the formula for D. This is an important formula. This is the central formula in power counting. Good. Okay. So now let's apply this equation. Let's see why it's so powerful. So let's say work with 5 to the 4 in D is equal to 4. So let's see what we find. So then D, remember D is telling us about how the divergence of a Feynman diagram. Okay. So D is equal to 4 minus E plus N into, so D is 4, 1 minus 4 over 2 is 1 minus 2. That makes it minus E plus N R times by D. That's, so if it's 5 to the 4, R is 4. Okay, so R times by D, this is 4 times 4 divided by 2, which is 8. 8 minus 4 for D, minus 4 for R. This is just 4 minus E. So let's see. If E is equal to 0, then we find that D is equal to 4. So an example of a diagram with no external legs is this Feynman diagram, and you can check that it does diverge as lambda to the power of 4. That's what we're being told. Then for E is equal to 1, okay, if there's only one external line, you're actually studying a correlator of 5, and that's 0. So this vanishes. So we don't need to worry about E is equal to 1. If we look at E is equal to 2, so by the way, this vanishing of an odd number of fields you've seen many times. One way that we argued it is if you're using the path integral, this is actually the path integral of an odd function. Okay, if you're using Feynman diagrams, if you draw a single dot, there's no way to finish off the diagram. When E is equal to 2, we would find that D is equal to 2. And an example of this would be this Feynman diagram. And you do indeed find that this behaves as lambda squared. So that also works out nicely. When E is equal to 3, well, this is a phi, 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 and this again vanishes, okay? You can't draw a Feynman diagram, or you're integrating an odd function. When E is equal to 4, then D is equal to 0, okay? An example of this would be this Feynman diagram. So there are 4 external lines, and this behaves like log lambda. We've already studied this one. So great, so that makes sense. When E is equal to 5, then we've got 5 fields, and this again vanishes. So we don't need to worry about it. And then when E is equal to 6, well, D is equal to minus 2. So that means it's convergent. Okay, the integral's convergent. So now let's just make some comments. Take a look. We've got 1, 2, 3. Okay, and that's all. Everything beyond this point is convergent. So we only have 3 divergent Feynman diagrams. Okay, so that's a finite number of diagrams that diverge, and that's why we could remove these with a finite number of matching conditions, and this is why, in fact, the theory is renormalizable. So now let me tell you why we say that D is a superficial degree of divergence. So why is D called the superficial degree of divergence? What did I call it? I called it superficial degree of divergence. Degree of divergence. Well, this is for 2 reasons. So first of all, when E is equal to 2, just the Feynman diagram like this, there is no integral. So there's no divergent integral. So there, our analysis led us astray, but that's fine, okay? It's just because there was no loop. So this piece that we're analyzing over here didn't even exist in that case. Then the second and more important reason why we call this a superficial degree of divergence. So if we take a look at E is equal to 6, E is equal to 6, this is meant to be convergent. And basically it's because this diagram is convergent, okay? So that really is convergent. And it's this diagram that is being picked up in the analysis that we did. But when E is equal to 6, we could also have this kind of a thing. We could have, let's see, let's take 2 legs over here. Let's put a bubble over there. Let's put 2 legs there. Let's extend this here and have 2 legs there. Take a look. There's 1, 2, 3, 4, 5, 6 legs. But if you study this carefully, this diverges like log lambda. So it is divergent. As one more example, you know, this also would be a 6-point correlator, but this would diverge like lambda squared. Okay, that's also got 6 external points. Now, what's going on? Well, basically, the divergences from lower diagrams, like the one for E is equal to 2 and the one for E is equal to 4, can be embedded into diagrams with a higher value of E. So when we say that now the Feynman diagram is convergent, we really mean there's no new divergences, but the old divergences can still appear. But luckily, these old divergences are removed by the matching conditions that we already have. So really, here we're counting the number of sort of independent divergences that appear, and we only have divergences appearing for E is equal to 0, E is equal to 2, E is equal to 4. Those can be removed by renormalization conditions, and that's ultimately the reason why the theory is renormalizable. Great, we'll continue in a moment.